Moving on to 20, it says which arrangement of 3 point charges at the corner of an equilateral triangle result in a zero electric field strength at the center of the triangle point B. So we have to have a look at these. So the electric field will all cancel out from each of these. Now, looking at the first one, looking at A here, because it's positive charge, your electric field for this Q over here will be directly out like that. It will be in that direction. For this one, it would be like that. It would be an equal length because this charge and this charge is the same and there's an equal distance. And for this one, it would also be like that. So I think you can see there that those three electric fields would actually cancel each other out, and so at that point over there it would be 0. You would have it as 0. So A is actually the correct one. You could try it out with all the others. You'll find that none of them will actually work, that they'll all cancel it out. Okay, so 20A. Going into 21, it says the mass of a planet is twice that of the Earth. Its radius is half, so we have the mass is twice, and the radius is half that of the radius of the Earth. The gravitational field strength of the Earth is G. The gravitational field strength of the planet is. Now we're actually going to be using this formula over here, the combination of these two. So we have F is equal to the universal gravitational constant m1 m2 over r squared, and G is equal to your force per mass. So we'd have to take one of these masses, say it's m2, and so we're going to divide this by m2 and it'll cancel. So it's equal to G is equal to big G m over r squared. So now that would be for the Earth. Now for this other planet, or this, it's the mass is twice that, so it's 2m, and the radius is a half, so it's going to be a half, and that will all be squared. So when I do that, I'm going to get, so let's call it planet X. So we're going to have 2gm over r squared, and we got a half squared, which is a quarter, and we know 2 divided by a quarter is 8, so we're going to have, this becomes 8 gm of r squared. So D would be your correct answer for that one. Alrighty, let's go over the page and see what we got here. Alright, so this is also dealing with magnetism. We're actually going to be using this formula over here. This one over here. This is the force on a charge moving through a magnetic field. Okay, so we have an electron enters the vacuum between two oppositely charged plates with a velocity v. The electron is followed by an alpha particle moving with the same initial velocity as the electron. The uniform magnetic field is directed out of the paper. So it says the electron's path is undeflected. The path of the alpha particle will be. Now there's two formulas that we're going to actually have to use here. We're going to use this formula over here, where F is equal to E times Q, electric field, and also that F is equal to QVB, sine of theta. This is the angle between them all seems to be 90 degrees, so we don't have to worry about that. Now they've got the same velocity, they've got the same magnetic field strength. Notice the mass doesn't come into play here, but the charge is different. For the alpha particle, it's a 2+ charge. For the alpha particle, you've got a 2+ charge, and for the electron, obviously it's a 1 negative. But because these two forces, for it to go undeflected, these two forces must be balancing each other out. The force due to the electric field must equal the force due to the magnetic field. And because you've got here that your electric field will be the force due to the electric field will be half, or just because you've only got one electron, half that of the alpha particle, but also half here. The alpha particle also will be undeflected. Both the force due to the electric field and the force due to the magnetic field will both be doubled, but they would still remain in balance between the two. Here we move on to the Geiger-Marsden experiment, and it provides evidence for the following. This was actually the Geiger-Marsden experiment was the one where they shot alpha particles at gold foil, very thin gold foil, and it provided evidence for this over here, that in the atom you had this dense positively charged nucleus. Before then they had this idea of the plum pudding, that the atom was made up of this doughy mixture of positive and the electrons were like scattered about. But most of the alpha particles shot straight through, but some of them shot back, and they could only have shot back if there was this densely positive charged nucleus. Let's have a look at 24. Now we're actually moving on here, so let's move on to this. This is there's not much in the way of formulas for the standard level for this unit, but you do need to be able to work with some numbers, but it's not too difficult. So we have 24. A radioactive isotope has a half-life of 2 minutes. A sample contains 16 grams of the isotope. How much time elapses until 1 gram of the isotope remains? Alright, so 16, it will go to 8, it will go to 4, it will go to 2, it will go to 1. So that's 2 minutes, 4 minutes, 6 minutes, 8 minutes. So it will be this one over here. Okay, pretty straightforward. Looking at this, we have data concerning nuclides are plotted using the axis below. What are the axis labels for this graph? So this is the y-axis and the x-axis. We have the binding energy per nucleon and the number of nucleons. This is actually the correct answer here. This is our very important diagram that we use. Going into this one over here, which of the following is true about beta minus decay? We have with beta minus, what happens with it is if you have x and it goes to y plus beta minus, it gives off also an anti-neutrino. And what happens if this is, say, let's just say this is 5 and 11, for instance. Because it's beta minus, you're actually going to have an extra proton here, so it's 6. One of your neutrons actually changes into a proton, but the atomic mass number stays the same. So an antineutron is absorbed. No, it isn't. It's released. The charge of the daughter nuclide is less. No, it's actually more. An antineutrino is emitted. That's correct. The mass number of the daughter nuclide is less. That's not true. It stays the same. So 26C.